In this video, we are going to talk about end behavior of polynomial functions. So to start off with, let's look at some examples of polynomial functions and take a look at their graphs. All right, so here we have the graph of a linear function, p of x equals 4x plus 3, which is a polynomial. It's called a linear function because its graph is a line. So, and here's a quadratic. The graph of that is a parabola, which we've talked about previously. Here is a polynomial function. It's a degree 3 polynomial. And you can see it's got kind of this shape where it goes up and flattens out a little bit and then keeps going back up like that. And here is degree 4 polynomial. Okay, and its graph. And here is a degree 5 polynomial and its graph. Okay. Here's the degree 14 polynomial and its graph. Okay. So if you go back and look at all of these graphs, right, one thing to notice about these graphs, it's what's called the end behavior. And basically what the end behavior is what does the graph do as it keeps going, x keeps getting bigger and bigger. In other words, as you keep going to the right, what does the graph do? And then as you go really far to the left, what does the graph do here? Okay, and so from what we know about a line is that the graph keeps going up and up. And here, right, as we go far to the left, the graph would keep going down like this. All right, on this quadratic, we can see this is a quadratic that opens down, right? So as we go really far to the right, is the graph going up or down? Well, it's going down. As we go really far to the left, right, is the graph going up or is it going down? It is going really far down, okay? So this one is going down on both ends. This one, right, as we go far off to the right, what is the graph doing, right? Well, the graph keeps continuing up in this manner. If we go really far off to the left, the graph keeps going down in this case. On this one, it goes up on both ends. On this one, it goes up on to as we go to the right, and it goes down if we're going off to the left like this. And this one goes up on both ends. Okay, so all polynomials, you kind of can see that what ends up happening is that the graph, as you go really far off to the right or really far off to the left, the graph either goes up or down. Okay, and they all do that. The left behavior is, what does the graph do as you go really far to the left? The right behavior is what does the graph do as you go really far to the right on the x-axis. All right, and so what we want to be able to do is just kind of determine the right behavior or left behavior just by looking at the graph of the not by looking at the graph, just by looking at the formula. It's pretty easy if you're looking at the graph to determine the end behavior, but just not looking at the graph, only looking at the function itself, that is not really super difficult, but we'll have to explain how that works. So first off is some notation that I'm going to use for end behavior. So for the right behavior, right, we'll either write one of these two things. As x goes to infinity, right? So if you're looking at the x-axis, it looks like this. So and this is x goes to, or tends to, is how you can read those little arrows. So we're going this way, right? Remember, x's values get bigger the farther you go to the right on the x-axis. And so here, this would kind of indicate the y values. So if we say as x goes to infinity, a polynomial function p of x goes to infinity, means that the graph is going to be going up, right, as we go off to infinity. Here, as x goes to infinity, p of x goes to negative infinity. So as x goes to infinity means that we're going farther and farther to the right, and then p of x, the graph, which represents the y values, that goes to negative infinity, means that the graph is going to be going down here. So this really just means as we go farther to the right, the graph goes up. This means as we go far to the right, the graph goes down. For the left behavior of a polynomial, right, we'll have one of these two things. Okay, so as x goes to negative infinity, so negative infinity would be smaller. As we go to the left, right, on the x-axis, the values get smaller and smaller that way. So this is saying as we go to the left on the x-axis, the y values, or the graph, right, goes to infinity. So that would mean that the graph does this, right, over on the left. It keeps, as you go to the left, it would go up. And on this one, right, as x goes to negative infinity, so meaning as we go really far to the left on the x-axis, p of x goes to negative infinity. That would be saying that the graph goes down like that. Okay. So one thing I have seen people get mixed up on this is confusing this with increasing, decreasing that we studied earlier. It obviously is a little bit related to that, right? And you can always phrase this, but for increasing, decreasing, what we studied before, the perspective is always from left to right. And so the end behavior doesn't always take that perspective. On these, it is, right? Because we're going in from left to right with these. But with this one, we're actually kind of going backwards here. So don't mix that up, mix those two things up, okay? With increasing, decreasing, the perspective is always left to right. But with end behavior, especially as you're going to negative infinity, going up far off to the left, you either say it's going up or going down. You don't give the answer in terms of whether it's increasing or decreasing, okay? All right. So on this slide here, we want to know, okay, we want to be able to determine the end behavior of a polynomial, not by looking at the graph, just by looking at the polynomial function itself, okay? And the secret to doing that is that the end behavior of a polynomial is completely determined by its leading term, okay? So the leading term, that's all you have to look at. You can disregard the rest of the stuff. The rest of it doesn't matter, okay? All right, so on the right behavior, right? So this is going to be for the right behavior. It's all completely determined by the leading coefficient. So whatever the leading coefficient is, right, if it's positive, then the graph is going to go up as you go to the right. If the leading coefficient is negative, then it goes down. Okay? So that's the situation. And the question is, why is that true? And for that, let's take a look at Desmos. Oops, wrong one. So when I first learned that fact, I was like, that can't be right, can it? Because, and my teacher said, well, it's because if you have a polynomial like this one, then that this leading term, right, as you go really far to the right or really far to the left, gets way bigger than these do, okay? So it doesn't really matter if these things. So for instance, this one, we would know that it would go up as you go really far to the right. And so you're telling me, and what I said was that, you know, the fact that this 3 is positive means that it's going to keep going up and up. despite what these other numbers don't matter at all. So I was kind of skeptical about that. In fact, I was kind of like, well, what if this is like some really small number over here, like 20,000x, right? Isn't that going to cause a problem? Because that's really small, a negative number compared to this, right? And you can see that it's not going to bother this thing at all. We'll have to zoom out a lot. Let's see. All right, that looks a little better. Maybe I made that number too big. All right, so you can see, no, it doesn't matter at all. That it's still going to go up. It's going to take it a little bit longer to do that, right? But it's still going to go up on the right, no matter how big these other numbers are. And the reason for that is you can see if you plug in powers of 10, and I'm going to take this back down. All right, let's make it 10 to the 0. Okay, and so if I do that, I plug in 10 to the 0, I get 2 here. And if I start increasing this number, right, 10 to the 1, and I plug that into the first number there, I get 3 times 10 to the 7th power. You can see that is already a huge number here, right? Okay. And then all of this does, right, when I have that. Sorry, let me do this to make it a little clearer. If I plug in a 10, I'll get 3 to the 10 to the 1 to the 7, right? If I plug 10 to the 1 in here, into this minus 2x, right, I'll get minus 20. So you can see that already this 10 to the 1, when I plug that in into this part, this number is way, way bigger than any of the other numbers, and 1 is just 1 here. So it is way bigger than any of the numbers there. And it just gets worse, right, the bigger this number is. If I plug a square in there, that is a 3, right, followed by 14 zeros. If I plug 10 squared in there, that's minus 200. So you can see this is dwarfing that, right? And even if I make this a big number, like say 20,000, right, this is minus 2 times 10 to the 6th right here. It's still way bigger than this number. And so you can see if I start plugging numbers that get bigger and bigger in here, right, into these terms, let's see. You can see that the numbers that I'm getting from the leading term just dwarf these numbers right here. This is a 3 followed by 35 zeros. That is an astronomical number, right? This is a negative 2 followed by only 9 zeros. So it doesn't really matter. These terms, when we're talking about the end behavior, what the graph is doing when we go really, really far to the right or really, really far to the left, it is all completely controlled by this leading term right here. Okay. All right. So going back to our slide here, how do we tell the right behavior of a polynomial? It's really easy. You just find the leading coefficient. If it's positive, then the graph goes up as you go really far to the right. If the leading coefficient is negative, the graph goes down as you go really far to the right. All right, and it's a little bit more complicated for the left behavior. So for the left behavior, what you want to do is look at the degree of the polynomial, right? And you can find that again by looking at the leading term. If the degree is odd, then the left and right behavior are opposite. So let's go back and take a look at a few examples of that. Remember, we had these graphs of polynomials. So on a linear function, the degree is odd, right? Because it's 1. And you can see it does opposite things, right? The behavior is opposite. 3 is an odd degree, right? So you can see it does different things from the right and on the left. 5 is an odd degree, right? And so you can see it does the opposite thing on either end. If the degree is even, then the left and the right behavior are going to be exactly the same. And so we can go back and look here, right? You can see the left and right behavior are the same. The degree was 2 in this one. On this polynomial, the degree is 4. You can see the left and the right behavior are exactly the same. On this one, the degree is 14, which is an even number. The left and right behavior are exactly the same. Okay? So that's the secret to finding the left and right behavior. I like to find the right behavior first, because all you got to do is look at the leading coefficient and then figure out the left behavior by looking at the degree. Okay. All right, let's look at some examples right here. All right, so state the left and right behavior. So it's going to be as x goes to infinity, p of x goes to blank. As x goes to minus infinity, p of x goes to blank. All right, and this is the right behavior, right? This is the left behavior. Okay, so first thing is the leading coefficient is this one right here, or the leading term. All the rest of these don't really matter for the left and right behavior. All right, for the right behavior, we look at the leading coefficient. It's positive, so it goes to positive infinity. For the left behavior, we look at the degree. It's odd, so it's going to be the opposite of this one. So that means if I graph out this polynomial, we're going to see that it goes up on the right, and on the left it goes down. And who knows what's going on in the middle? That's a little bit more complicated. All right, and so there you can see, right? That's what the graph looks like. This ancient graph that I drew years ago. All right, in the next example, again, it's going to be as x goes to infinity for the right behavior. P of x goes to blank. That's the right behavior. On the left behavior, as x goes to negative infinity, P of x goes to blank. Oops. Okay, so again, what we need to do is find the leading term. The leading term is right here, x to the 6th power. And the coefficient, leading coefficient is 1, which is a positive. So that means on the right behavior, it goes up, right? So the graph looks like this on the end over here. And then the degree, for the left behavior, we look at the degree. It is an even number, so these are going to be the same. So it does this on this end over here. And again, in the middle, who knows? That's complicated. We haven't talked about that yet. So we don't really, just from here, we don't really know yet what's going on in the middle. We're just talking about the end behavior. All right, and there we go. You can see it goes up on either end and does some stuff in the middle. Again, we have yet to figure that out. All right, next example, as p of x goes to, as x goes to infinity, p of x goes to blank. As x goes to minus infinity, p of x goes to blank. This is the right behavior, left behavior. All right, so find the leading coefficient right here. All right, and then for the right behavior, all we have to do is look at the leading coefficient, which is -3. It's negative, right? So it will go to negative infinity. In other words, when we graph this thing out, we're going to see that it goes down on this end. All right, and then for the left behavior, we look at the degree. It's an odd number, right? Which means that the end behaviors are going to be opposite. So this one will be positive, the opposite of that one. So on the left end, as we go far off to the left, this will go up. All right, so here's what it looks like, and there you can see. Again, the end behavior doesn't tell you what happens in the middle. That's more complicated. All right, now they want to state the left and right behavior of this function, right? And so now we're kind of in a bind here because this is in the factored form, right? This is written as multiplication, minus 3x times x plus 2 times x minus 4, and not in the standard form, right? So that trick I showed you about multiplying the leading coefficients is helpful here, right? If you multiplied all this out, we know that it would be like minus 3x times x, which is the leading coefficient of our leading term of this polynomial, times the leading term of this polynomial, right? And then plus some other stuff which we're not going to work out. So we know that this polynomial, if we worked it all out, would be minus 3x cubed, right? Plus some other stuff which doesn't really matter for this particular problem. Now it does matter almost every other circumstance. So I don't think you never, have to do this. It's only for this problem, right? We're only looking at, and that's the left and right behavior, we're only looking at the leading term, right? So, and so we're good. We have that figured out. So as x goes to infinity, we can say p of x goes to negative infinity. Why? Well, we know the leading term is minus 3x cubed, and that's a negative number, right? So the leading term is a negative number, so p of x will go to negative infinity. So when we graph this out, we'll see it going down like this. And so that's the right behavior. For the left behavior, what we want to do is look at the degree. The degree of the polynomial is 3, which is an odd number. That means that the end behaviors will be opposite. And since this one is negative infinity, that means this one has to be positive infinity here. And I drew this in the totally wrong spot. Sorry. All right, the original one should have looked like this, right? As x goes to infinity. This goes to negative infinity. Okay. And on this one, as x goes to negative infinity, p of x goes up like that. All right, I think that is it for this. Oh, actually, here's what it looks like, right? Yeah. Again, the end behavior doesn't tell you anything about what goes on in the middle, like that. All right, that's it for this video. In the next video, we will talk about zeros of polynomials.